This video is going to cover shear flow. Shear flow is the shear force that we have per length down the longitudinal axis of the member when you have connected parts. And it has two equations really. Shear flow is little q here, and that is the force of the connector per the spacing of the connector, or it's also equal to the shear force V down the face of the member times Q over I being the moment of inertia about the neutral axis for bending. So again, this looks very similar to our transverse shear stress, which was VQ over IT. And yes, they are related. Effectively, little q is the shear stress times the thickness at that spot. But specifically, we're not really talking about like maximum shear at that spot. We're talking now connecting pieces. So we're building up shapes. So instead of just having a hot rolled I shape made out of steel, we're going to take boards and create an I shape. Or instead of just having a rectangular tube out of steel, we're going to build one out of, say, wood. And then obviously when these things are built out of individual pieces, we have to connect them with either nails, bolts, welds, glue, or something. So we're going to use these two equations, and this time Q here is just a little different. Q is going to be, again, it's the same kind of Q that we had before, that A prime times Y bar prime. However, this is for the connected area. So we're very specifically looking at the transverse and longitudinal shear through the connection of the multiple parts. And it's going to make a lot more sense when we do some examples. So in this example, we have an I-beam that's made up of 5 boards this time. You might think this is probably the stupidest way possible to create an I, and I'd probably agree with you, but that is the shape that we have. So we have one big rectangular member coming up kind of vertically there, and then we have 4 itty-bitty little cubes that we're going to stick on the sides to try and make the actual I shape. Now, of course, because we have 4 cubes, we have 4 nails, and we want to find the spacing of these nails to the nearest ½ inch. Now, the spacing of them, we are going to be talking like down the axis of this member. So from the top, this looks kind of like this. You know, from the top you can see the total size. Well, actually, it's going to be visible lines. So we're going to see those 2 pieces connected on the top there, and our nails specifically are coming this way, kind of along the member, and this is the spacing that we want to find for those nails. Again, on each side. But that, I figured that's kind of a given. So anyway, we're going to find that spacing of the nails down the axis of this member. So we have our dimensions for it. The problem does give us the moment of inertia about that neutral axis, and that's 20.58 inches to the 4th. We have a shear force across the face of the member of 30 pounds, and they give us an allowable shear stress of the nails, and that's 13 ksi. And we also have a nail diameter of 1/16 of an inch. So in order to find spacing, we're sitting here thinking, okay, well, spacing, we're going to use shear flow, because welcome to the shear flow video, right? And that's going to be the force of the connector divided by spacing, also VQ over I. So things we know V is given right here, 30 pounds. We know I is that kind of purpley color up there, so we'll just highlight him in purple here. So we have I. Q, again, he's going to be kind of weird, but what I don't have is the force of the connector. Like, where is he? But we do actually have this information given over here. And let me remind you that, again, shear stress was equal to the force parallel over the area. parallel, right? So effectively, we're going to be going back to our like design of shear connectors where like we had a pin and it was in single shear or double shear, that kind of thing. So again, we're going to be going back to, we have two members, and we had, before we used to say that there was bolts coming through here, but now it's a nail. So again, we only have one shear plane. And remember that that was literally just, we used to call it V because, you know, that was our shear force. But this is our force of the connector now. So it's the same equation we used before, except we just have to find the force of the connector. So we had an allowable 13 KSI is equal to this force I want to find divided by the area, and they gave us a diameter of 1/16 of an inch. So that's pi over 4 times 1/16 of an inch squared. So we're going to get that the force of our connector, our nail here, is going to be equal to 39.9 pounds. So okay, cool. We have that. We want to find spacing. That's great. Technically, we do not actually need to solve for Q in the slightest. We can just relate those two other equations of Q together, and that will be good enough for us. So the last question is, what about capital Q here? What about that first moment of area? And when we did it before, it was taking it at a specific point, and you said, hey, I want to find max shear that's at the neutral axis. Q is, of course, the area away from the neutral axis at that point. But since we're talking about connectors and shear flow, we're going to have to change our mindset about where we're looking at. We're technically looking at the plane connecting the two members. So if you were going to say, hey, I want to find maximum transverse shear, you'd be taking it along that plane. Now that's not a horizontal point, so you might be thinking, okay, we gotta completely rechange our mindset on it, and technically we don't. Technically we don't, because in this regard, Q changes. So I did tell you that at the beginning, Q is gonna change. So what Q is going to be is the area of the connected piece. So Q is gonna be the connected area. The connected area. And you can do this in kind of like one of two ways. You can say, hey, I've got one nail here in this one area, or you could say, I've got two nails and I've got two areas. You're going to get the same answer either way, because you either have two forces in two areas, or you have one force in one area, and they're going to, go figure, kind of magically cancel each other out. So however you really want to do it is kind of up to you. So on this one, I'm going to just say I have one nail and one area. Okay, so to find Q, I guess we'll continue to do it in red here, I guess. To find Q, I'm going to need that area prime times, of course, y bar prime. So our area prime is going to be simply this area. And y bar prime is going to go from the center of this area down to the neutral axis. So that area, we're just going to have to, I guess, assume in this case that the boxes on each side of the eye here are actually the same width. And that would be a width of 1. 3 minus the middle web of 1 is going to be 1 on each side. So the area is 1 times a half. So 1 inch times the 0.5 for the height. And then y bar prime is going to be the distance down to the neutral axis, just like before. Our neutral axis, because this is a symmetrical shape, is going to exist midway vertically in this shape. And we have a total height of a half plus 4 plus a half, so a total height of 5. So that's going to be 5 inches divided by 2 to the neutral axis, but minus this little itty bitty top distance right here, right, which is going to be half of half. So minus 0.5 inches divided by 2. So that's our y bar prime. And what we're going to get for Q Q is then going to be equal to 1.125 inches cubed. So what we can do now, we have Q. Q is now solved for. We can put him in red now. So ta-da, so we have all four pieces. We have the force of the connector, he's right here now, so we have him in blue. V was given, I was given, Q we just solved for, so now we can solve for spacing. So I'm going to rearrange the spacing equation, and I'm going to get force of the connector times I divided by V times Q. And all I did was simply rearrange this equation. So I multiplied, I did my cross multiplication, and then I moved the VQ to the other side, and that's how I got this equation. Nothing really magical. So again, I'm going to get the force of the connector. We solved for that. We said 39.9 pounds. Then I was given to us, I up here at the top, 20.58 inches to the fourth. And then divided by V, they gave us a shear force, right? They said 30 pounds for our shear force up there. Then Q, we just literally solved for Q, so Q right above us there, 1.125 inches cubed. So as you can see with our units, just to get another fun color in here to cancel this, pounds are canceling, inches cubed are canceling, and you're just going to have inches to the first. So yes, spacing is in inches. So our spacing is going to be 24.4 inches. Now, they had a little caveat up here at the top. They said to the nearest ½ inch. Now, you can't just round to whichever one's closest, right? Your options at this point are 24.0 or 24.5 inches. And you can't just go, yay, this one's closer. That is definitely not what we're going to do. Effectively, what we're saying is we need nails every 24.4 inches. We need to have a nail. If you put a nail every 24.5 inches, you're kind of failing the requirement here that it needs to be at least every 24.4. So technically, our correct answer is going to be 24.0 inches. If you want to think about it another way, you're thinking, okay, I need to have nails every 24.4 inches. If I space them a little bit closer, if I came in with my answer and said, okay, my nail is going to be here and I'm going to space it just a little bit closer, at the end of the day, I'm going to end up with more nails than what I originally needed. And that's always a good thing, right? More nails, more connectors, more connecting force is definitely a good thing. So this is why we definitely need to round down when we come to spacing. So hopefully that makes it make a little bit more sense, but why not? Let's do one more. So this time we have 2 nails across the top. We have a wonderful little box here. It's a built-up box, and it's 2 inches tall for each one of these things, and a total length of 9 across it. So, 2 minus 9 is 7. So we have this cute little box made up of 1, 2, 3, 4 members, and we have 4 nails, 2 on the top, 2 on the bottom, 1 on each side to connect into those vertical pieces. So each nail can support a maximum shear of 15 pounds, and we want to find the maximum spacing of the nails on the top, because it's pretty much going to be the same on the bottom in this symmetrical case, so that this beam can support a shear force of 100 pounds. So first things first, let's make heads or tails of what we're actually given. We are given the beam supporting a shear force of 100 pounds. That means that V is 100 pounds. So we have a shear force going across this face of 100 pounds. Each nail, though, each nail supports a force of 15 pounds. That is the force of the connector per nail. That's 15 pounds. So again, I want spacing. How do I find spacing again? Shear flow. Shear flow is force of the connector divided by the spacing, and also V times Q over I. Okay, what do I have? What am I missing? I have force of the connector. That was given this time, 15 pounds. I want to find spacing. I don't have spacing. I have V. V is the force of the beam. I don't have Q. I don't have I. Can I solve for those? Yes. Let's first start with I. So for I, moment of inertia about the neutral axis. Conveniently, the neutral axis is going to be where? At the dead center of this thing because it's symmetrical? Yes. So technically you might be thinking, oh my gosh, I have 1, 2, 3, 4 rectangles. This is going to be a really long equation, but let me remind you of something that's really cool when it comes to moment of inertia, that you can add and subtract shapes. So how I'm going to solve for this is I'm going to look at it as though I have my really big square, and then I'm going to minus out the small square. And the reason I'm going to do that is because both the big square and the small square have their centers at the same exact point, which means when I'm solving for moment of inertia, I am not really having to use parallel axis theorem because the center of the whole shape is at the center of the big one and at the center of the small one, so it's the exact same point. So it's literally just going to be 1/12 base times height cubed of the big one. So the big one is 2 plus 7 and 2 plus 7, so 9 inches and 9 inches, minus the small one's 1/12 base height cubed. So the small guy is going to be 5 by 5. So 5 inches by 5 inches. Technically, 7 went all the way to the outside. We need this inside. So it's all symmetrical. It's all 2 inches. So 7 minus 2 inches is 5. Same thing this way. 7 minus another 2 inches is 5. So moment of inertia, in that case, really, really simple. So the moment of inertia that we're going to get for this is 494.7 inches to the fourth. So really, actually, not quite so bad. So now the question is, now that we have moment of inertia, we've got this guy now, there he is. What's Q? What is Q? I guess we'll do him in purple. So Q here is going to be in purple. What is being connected? So what is being connected here? I don't know if this is going to be possible to actually draw this without making a giant mess. What's being connected here is this part. So that piece is being connected. So again, the area of the connected piece times the distance from its center down to the neutral axis. That's going to be y bar prime. So again, we're going to have our area prime, and our y bar prime does go from his center, who is, in line with that, down to the neutral axis. Okay, so first things first with Q, I need area prime, and I said y bar prime. So how about area first? Area of that shape, a grand total of 9 wide and 2 tall. So 9 inches wide by 2 inches tall, that's area. Next, we need y bar prime, the distance from his center to the neutral axis. Okay, so from the top down to the neutral axis is what? Half of 9 inches. And then the distance from the top down to his little center is half of 2. So I'm going to have half of 9 minus half of 2 inches. Multiply those together, and we're going to get Q. And Q is equal to 63 inches cubed. So looking at our equation, we've got all of the things, correct? So let's solve for spacing. Spacing is going to be f of the connector times moment of inertia divided by V times Q. Force of the connector, we said 15 pounds per nail. How many nails across the top? 1, 2 nails. So we have 15 pounds times 2 nails. So again, this is the number of nails in the connector. There's 2 nails in this board that's being connected. Okay, we said I. They gave us I, yes. No, we calculated I. I was 494.7 inches to the 4th divided by V. V was given. V was 100 pounds across this beam. And then Q. Q was, we just calculated it, 63 inches cubed. Okay, so solving for this baby, we're going to get that the spacing is 2.36 inches. Nobody, when they're going to put nails in, is going to measure to 2.36 inches. So again, if we had to go to the nearest 1/4 of an inch, what would we use? Again, if you need at least a nail every 2.36, then we're going to use a spacing of 2.25. This will give us more nails than what is necessary, which is always a good thing. So hopefully, between those two examples, shear flow doesn't feel quite so terrible.